Good morning. I'm Andrew Collier, and I'm going to be chairing this session. We've got one standard talk followed by 3 lightning talks. And the first speaker this morning is Giovanni Ballarin, and he's going to be talking about doing a faster macroeconomic modeling using GPU acceleration.
Good morning, everybody. So I'm Giovanni. So I am a Master of Science student at the University of Wisconsin in double degree program with the University of Tor Vergata, and I study economics. And so today we're going to have some fun with GPUs and macro models. Well, simple macro models really, but you see. So first, a disclaimer: I am not a programmer, not in the sense that some of you may interpret here. So some of my code might be terribly ugly, because well, that happens. I just saw the talk on the arrays, and I'm not doing things that way, so it's probably very, very bad. And so if this causes you discomfort, just look the other way. or come back to me and tell me what I'm doing wrong so that I can learn something. That would be great. Any comments will be appreciated at the end of the talk, so thanks. So all the code actually is, I'm going to show you some code, but all the code is much more complicated than that. So if you really want to follow along, afterward or right now, you can go to my GitHub page, and this GitHub page you also have the presentation, but most importantly, you have the iJulia notebooks with the code, the working code that I'm going to show you. So there's that. So I'm going to start with a simple value function introduction on dynamic programming as a concept and how we use value function to solve dynamic programming problems, and then I'm going to do I'm going to move the VFI problem from a theoretical problem to a computational problem, and I'm going to use Julia, simple Julia, to do it. And then we're going to start using OpenCL, and then that's going to be not nice. And then we're going to do GPU arrays, which is like 2 thumbs up. We're going to have fun. So let's start with value function. So value function iteration, also known as value iteration, is probably one of the most common ways to solve dynamic programming problems, at least when I do it in my models. Dynamic programming, I guess most of you, if not all of you, know what dynamic programming is. It's a framework of mathematical optimization that is very much used for control theory programming, and in my case, economics. And the traveling salesman problem, it's an example of it. But we're not going to do that today. So value function is actually not the only way of solving dynamic programming, but it's a good way because of the contraction mapping theorem, which tells us that value function iteration, if there is a solution, it should converge. And it doesn't even matter where you start from, but it's going to converge eventually if you give it some time. And the generic problem is what we see here. So it's a maximization problem, and at every iteration we have to maximize a utility function of the current actions and the states, and then we weight the previous value function, but we optimize over the space of the action, and by this way we find the next iteration, and we keep doing this until we converge. And thus we can define an operator that we're going to call T, and this is the value function iteration operator. And so the algorithm for the VFI is incredibly simple. It just fits in one slide. You start with initial guess. Usually you can even set the entire value function to be 0 over its domain, and then you keep iterating, and then you do the differences between the 2 value functions. And if it suits you and you think that the difference is small enough, then you just stop, and that's your approximation of the solution. Of course, V is a function, and so this is computer, and this is numerical programming and numerical computing, so we can't use really functions, but we're going to approximate the infinite dimensional thingy with a discretization over the domain, and we should discuss about how we should discretize value functions, but maybe we're not going to do it here because it's a complete problem on its own. So we're just going to assume, I'm just going to assume that an even discretization of the domain, it's good enough. So the good is VFI practically solves all the problems, at least for me, it solves practically all the problems. Always converges if a solution exists in a standard framework, in the standard framework that we will consider. It's easy to grasp and straightforward to implement, which are all good things. I mean, if you add a stochastic component, at least to the models that I consider, then it's going to get a bit iffy because you need to increase the number of value functions that you're considering, and depending on how many state variables, this increases the complexity of the problem a bit. So yeah, but the very bad part is that it suffers from the curse of dimensionality, and I'm going to do it more into details on that one. So in Julia, we take a benchmark model, which is the real business cycle model. It's a really, really basic thing. And it requires a numerical tools for a solution. Note that there's a small asterisk there. It's like it requires it for some values of some of the parameters. There is actually some parameterization of the model allows you to find an analytic solution. And so you can actually compare and benchmark whether the value function actually works. And so the features of the RBC in itself are an aggregate economy. So we have agent consumer, which are consumers, firms which do production, and it's very deterministic. So it's a problem of, it solves an optimization problem for an agent who actually lives an infinite amount of times. It's very sketched, and you can see that there's a function. We call it CRRA function of consumption, and then future consumption is weighted with an exponential term, so it's a series. And then everything is homogeneous, so capital, consumption, production, they are all the same thing. You can just write that one constraint right there. And this is the Bellman equation, which is how we formulate the problem so that we can apply value function iteration to it afterwards. So the VFI for the RBC model is actually quite simple. So you can see it's we fix a discrete grid for capital K, and with a set number of big NK points, we set I equal to 0, so we're iterating. Then we set a precision that we want to do. We want to run the problem with. Then we make an initial guess, and we just keep iterating. And you can see here that for each point on the capital grid, we have to compute. This is the easy way of unpacking that maximization, right? Because maximization is not a transparent operator. In this case, the maximization means that we have to compare all the possible combination of present capital and K prime, which is future capital, the future capital choice that we can make. And we have to make, in this case, a vector of options, and then we just have to find the maximum of this vector. And this is going to be the next iteration of the value function. And so this is how we unpack it. And then we just keep doing this for every value, and we keep doing it until we achieve the required precision. The Julia code is straightforward, just what I said before. Just you will use the logarithm, which is a specification of the CRRA for a sigma that goes to 1. And this is, as you can see, I'm not optimizing really well the code. This is just you could do this in basically any other programming language that is even not Julia, and this is very intuitive. So there are some issues. It's not optimized. We're not vectorizing anything. We're not even using the max operator, which in Julia, I guess it's much faster than me iterating over the entire array and computing the single value and then comparing them and storing them manually. So vectorization is key for performance, and you can get much more performant programs. I myself don't use that kind of code. But the fundamental issue is that as soon as I increase the grid, let's say that I double the number of points, since I have to compare every present with every possible future. This is going to increase quadratically this problem. And this doesn't scale well because approximation, we can do linear approximation and we can do polynomial approximation of the value function, but at some point, if the function is not a good function, the approximation is going to break, specifically for usually the boundary the boundary location, and so we're going to have an actually big error once we simulate the model. And so we can vectorize operation, we can pre-compute stuff, and Julia allows us to do very cool stuff. It does itself cool stuff. Like, for example, I'm sure that some of the, for example, the numerical instructions are now actually done in SIMD automatically, but I didn't really look that much into it. And so, of course, if you do this, then you're going to get much nicer returns to the investment of actually doing this optimization. But the speed up falls flat very early on because simple of the combinatorics issue, combinatorics nature of the problem. So, well, let's turn to something else that works for graphical. So, right, GPU generic program, generic purpose GPU computing, they cannot replace our workloads. In fact, they can't run. They just run graphical stuff. But superior performance is one thing they're good in embarrassingly paramathematical tasks. And economists should be interested because you can have incredible speedups, at least for something like matrix algebra. GPUs are done for that because that's what you do when you have to do rasterization and projection and stuff. So if you can't use the same type of parallel structure for these kind of problems, we can actually have better returns to better performance. And this can be done for value function iteration, of course. Monte Carlo, repeated games, and the example I'm basing this talk and my work on is this paper from 2001, Topping a Supercomputer Under Your Desk, when they found that with 65,000 capital points, which is a lot for a capital grid, it's roughly 509 times faster, which is, well, very good if your model is even a bit complicated, because 509 times means if before you had to solve a problem and sometimes some economical problem take days to solve. Now you can do it in hours or minutes. So this is a completely incredible return for most of us. And of course, we have a limit, which is given by the simple very basic Andam's law. It tells you that whatever serial part of your algorithm it's in there somewhere, it's going to be the one that's gonna dictate how much returns you can have for your parallel algorithm, because that's going to remain serial, and you will not see returns on that part. So you can be as fast as you want, but if you have a very big serial part, it's not going to help. The parallelization is not going to help you. So of course, VFI is compatible with GPUs, and yes, it works. And especially well suited, because if we go back, we can see that we are doing the same thing identically the same problem is run identically for every combination of points. So specifically in this case, for every point on the capital grid, we're doing the same optimization. And they do not intersect, so we're not interested in how we optimize the next 10 points. We're interested in where we are now and where we're going in the future, but where are other people, it doesn't interest us. And so yes, we can, since we can parallelize all of this. So for every k, we can parallelize the optimization problem, and we can optimize the iteration problem. And so Julia makes it easy, actually, to use the GPU because of the many packages of the Julia GPU group. And this is what brought me to it, because it has interfaces for CUDA and OpenCL. And this is not normal, like in the panorama of like simple numerical package to be so easy and so open. Like, I'm not making any name, but I like MATLAB because I use it, but OpenCL doesn't work in MATLAB. I mean, you can try, but please don't, because it's bad. OpenCL.jl, in fact, allows you to write kernels directly, and then just plug it in, and they're going to work with your Julia code with some glue code. And so we make it such that each thread on our GPU solves for a single K. And this is the kernel, which is ugly, unless you like, I mean, not ugly. There are some C programmers who really like this. But if you want to, like, from my point of view, it should be easy. We should be able to do one whole program that does everything, and it's transparent. And this is not transparent because we have to move to something else. And this is being able to write GPU kernels is a completely different set of skills than being able to do something, solving economics model. It's a skill in its own. So this is the Julia code that works with that code. And so you can see that we're using OpenCL. We do the K-grid, but then we have to create a device, a context, a queue. We have to use float32 because, well, at least on my GPU, float64 are not supported, so we have to restrict our types. We have to create buffers. We have to copy stuff into the buffers. We have to create the program. We have to compile the program. And then we have, in the while, we have to push it into the queue, read the results, and then compare them, and then keep doing this. And this, I mean, it works, but it took me a lot of tries to get this working right. Does it work? Well, we're here, so it does, I guess. This is the theoretical solution. So as I told you, there's an analytical solution. And these are, I mean, if you can tell the difference, I cannot tell any. I don't remember which one is the CPU and which one is the GPU result. So it works in the sense that it gives you the same answer, basically. Even though you are using float32s, it converges to the same result. And, oh, sorry. Is it faster? Well, yes, of course. If we're here, I mean. It's 25 times faster, which, I mean, the scale of the problem is very small, so returns are not going to be super duper returns, but it's faster. And this is run the second time, because the first time you're going to incur into the fixed cost of moving stuff to the GPU, compiling the kernel, like moving it to the GPU, et cetera, et cetera, et cetera. So, yeah. Is it nice? No. It took me 2 weeks to get the thing working, and you can see that the lines of code are actually it's a very compact thing, but you have to write OpenCL code, and well, you first know how to do that, and then you have to debug OpenCL code because it's going to debug it in its own when it compiles, and you have to debug Julia code that glues in the OpenCL kernels, and then you have to start all over again until in some way you get to something that works. So Julia being Julia, there must be a better way, because there must be. It's its beauty, right? And yes, there is. It's very beautiful. GPU arrays.jl is, I cannot stress this enough, it's awesome that you can, I mean, for me, it was awesome discovering that you can actually work on arrays on the GPU, and it's like transparent, so transparent. And you have actually CL arrays, which GPU arrays is abstract, but CL arrays allows you to transpile everything into OpenCL, and it just runs, it works. And everything can be done in Julia. So the code that you use, there's no more glue code. All the code is in one place, in one language. So now we consider RBC with uncertainty, which is a bit more complicated. I did not even try to write an OpenCL kernel for this case because I don't want to do that. It was already too much of a complication, because now we have a random process, and so the expectation now, it's a real expectation. We have to, the future is uncertain. We have to consider all the possible future possibilities, and we have a transition matrix, because usually, if we consider Z as a Markov process, there is a transition matrix for this process, there is a number of states and Z, and so the agents must weigh all these chances. And even with the small complication, we are already multiplying our problem, because depending on the future that you're looking at, depending on the state you are in with that Z, you need a different value function. You cannot just reuse one for everybody, because multiplicity of options, right? So Z is an approximation. Usually you can even have 10. So 10, this is done with the Tauke method, so you can approximate a continuous process by, I don't know, 10 states and a Markov matrix, but that already explodes the problem and in complexity, right? On the CPU, we just keep doing what we did. We create now a matrix which holds, for example, in rows our thing. and then we just add another loop outside. And here, we compute from consumption for all possible k's. So now we have to redo the same thing. They're just at z multiplying it. And then we have to find the maximum of the value function. And the only difference that we're doing now a dot of the matrix times the value function, because we are weighting the chances of incurring in the specific future given our present state. So the transition from the present state to any possible future state. And with GPU arrays, is this going to be more complicated? Well, a bit, yes. You have to tell Julia that you're doing stuff on the GPU, so you're using CL arrays. So everything is a CL arrays. It's going to be defined on the GPU. And then you have to write this nice, bit verbose, but nice GPU call. And you put inside the matrix that is going to be, say, the leader, so the one over which you are actually iterating, so that you can create a linear index that tells your position on the elements of the matrix. Then you have to push in all the float or int, or you have to specify the type nicely so that it works on OpenCL, all the arguments, and then you have to do this do. And inside you have to write the kernel. But what's going inside that kernel? It's the same code, mostly the same code. You have to do some changes because it's not going to be the exactly the same code. But instead of doing a for now, you have an IDX that is given by the thread, so the execution thread that you're using, and that's it. You just have to access the element with that ID. So GPUs arrays actually allows us to do everything in Julia. So if we add the code, we can just use it much easily and port it to the GPU with relatively zero effort, or really close to zero effort. And the question is this still fast? Is there some overhead? Is this like, is this good enough for us? Yes, it is. It's 6,000 times faster. This is again the second time that we're doing this. So the first time you have to compile everything, and actually, I mean, I love the CL arrays package. It works, but it's transpiling OpenCL, so it's going to take some time to take Julia, transpile it to OpenCL, and then do the compilation, then coming back. It's a bit of a monster, but it works, and the work behind it, it's incredible, and it gives you returns. It works, and it works very well. But we might want to do something even more complicated, and this is OLG models, and this is what I do in my line of work now. And you have a lifetime of an agent, right? And you have to solve t, if t is the number of years that this agent lives, so it's not living anymore an infinite life, then you have to solve t value function, because given your age, you might want to optimize differently, right? So you have to solve it by backward iteration. You start from the last period, and you go back, right? But because you want to add in other, like I want to add in other things, for example, so capital, human capital, ability, the number of points that you have to go through and the number of combinations of present versus future that you have to go through is in the order of millions of points. And then for each of these ones, you have to do a maximization over the possible future state. So this thing grows in complexity very, very fast. And so also sometimes, most of the time, convergence is required. So you don't solve the model once. You have to solve it, you simulate it, and then if what you get is not the same as the theoretical result that you can get from the equations of the model, then you have to keep doing it, and some parameters have to be changed or tuned, and this may take hours or days if the model is complicated. But using the GPU, since the kernel is the same, well, we have this cost of initialization and compilation that is fixed, but we have to run the same thing many, many times. So if everything fixes on the GPU, which well depends on what GPU you're using, the cost is incurred once, and so you can do it very, 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 very fast once you do it once. And yes, and so in my description of this talk, I promised you a big thing, right? So a complicated model that can be solved with 500 times faster and go from hours to minutes. And I did that, and it was wrong because I was aggregating wrong. So there was an error, there was a mistake. And what actually happens when I corrected my code in the simulation step of the model, it happens this. The solving is very fast. The GPU is thousands of times faster, but my simulation is very inefficient. So you have this, if you do a simple model, of course, and the solution of the GPU takes 0.01 seconds, and the CPU takes some seconds, right? The fixed cost is not going to give you the same returns. What you have, like, to get the same, from 150, you just increase the number of points until the GPU is, until this fixed cost, it's a fraction with a fixed point. You can get there. You actually can get to any type of, so this is 3 times better performance, but you can go from 3 times to, well, if this scales linearly by increasing, you can get up to very close to 2,000 times faster, I guess. So it was a promise. It's now broken. I lied to you. I'm sorry. But yeah, happens. Sorry. So does it work? Well, relative errors of value function are small, at least in the RBC with uncertainty. Unfortunately, in the OLG model, I'm still working on it because there is a bug that I'm still trying to track down. In the GPU solution, there's a problem, and so it's still in experiment. I marked it as experimental, but the solution, yes, is preordained, assuming that we're doing things good, and this is okay because even if the GPU kernel doesn't meet the exact same result, I know that the operations that are executed are those because it gives me our result. It just maybe some parameters is off. So it's 3 order of magnitude faster anyway, even if it doesn't work. Sorry. And so Julia plus GPU arrays is actually a breeze compared to doing all the nitty-gritty stuff. I mean, I have respect for the people who can do that. I can't, so I use this. And the conclusion then, what can we get from this? Well, first, if parallelism, if possible, take advantage of it, this should also have a remark. It's like, if it's faster, probably. Don't parallelize everything just because it's a buzzword that you heard it in my talk. This is like an experience of what happened to me. It's like a field journal of somebody who's reckless enough to do this kind of things, and happens to study economics too. But you could try. So I mean, as a general remark, yes, if for problems parallel, maybe it's better to parallelize it. GPGPU brings big returns. Again, if you're lucky, if you code it well, if that's your, and potentially it brings you big returns. And in Julia, well, writing kernels is actually so much nicer than getting your hands dirty with actual GPU kernel code. My final remarks are for economists, which I know is my kind of. And be bold, and like sometimes we use a lot of very, I have professors who use Fortran still because it just works. It grows faster than I don't know that whatever tool chain you're using. But Julia is fast, and it's also nice, and I can read it too because I can't read Fortran. It's like Chinese to me, and so yeah, this is what we get. I just want to acknowledge Simon Danish, who is the awesome guy behind CL arrays and transpilot.jl and GPU arrays. He's the main guy between this, and he makes everything possible. So he's awesome. Go check his things. So thanks.
Thank you, Giovanni. Questions?
Thank you. I have 2 questions, if I may. The first one is, you mentioned in the beginning that the algorithm is guaranteed to converge.
Yep.
Is that still true after these discretizations and other approximations that you make?
Yeah. So that's a good question. Well, yes, value function iteration. If the problem is not that it doesn't converge. The problem is that if you discretize wrong, it converges to something, but that's not your solution because you are approximating. So that's why they said that discretization is an issue. I didn't talk about it, but it is an issue. And usually when you do these things, like in my class of computational economics, they say you should use some kind of interpolation because you should always then move smooth. Once you do one approximation, you should be able to, when you use the future possible values, you should not restrict yourself to the grid. You should smooth things out, and this gets you much more precise results for the same cost, really, because interpolation is not as costly as increasing 10 times the size of your grid.
Right. Thanks. And secondly, you mentioned in the end that your speedups are limited by the simulation part.
Yeah.
Could you elaborate on that a little bit? Because normally simulation is the most embarrassingly parallel thing that you could have. So where exactly is the limit?
I prepare for that kind of thing. You want to look at the code, right? Should I? Sorry. I want to look at the code. So this is that's why I didn't show it to you, because this is ugly. Like, this is the GPU kernel, but the simulation is a bit long. It's here. So the problem is that what I was doing before here, this is the slow part. I was, semicolon was here, and now I moved it here, and now it's slower because I'm doing more operations. This is a distributional model. There's a distribution over the set of states, and to simulate the model, you have to bring the distribution forward, and that's costly because you have to, for each possible state, you have to consider all the agents that go into that place, and so the operation, at least in the way I did it, it's inefficient. It's expensive because it's a lot of small matrix operations, but since there are so many, it takes lots of time. And as you can see, it's also like right now I'm doing it in a nested loop, which is a very bad idea. So yeah, that's why it's slowing it down for me. But I guess it's not true in general.
All right.
Thanks.
That's the comment of this. But the reason probably is that the column is in the middle column, so you have a strike in the assignment. If you move this column, it might be just faster by rearranging how you organize your array.
Yeah, no, definitely. Just that I haven't explored it because it's a bit of an intricate. It's a bit of a this is, if you want, I encourage you to go through my code and be like, oh, this should be done differently, because for me this is a monster a big thing. So you can see that many things are going on, and the kernels are not really immediate grasp. It took me some time to put them. So yeah, thanks for any comment on that.
Great. Thank you, Giovanni.
Thank you.